So we're going to talk about a position, velocity, acceleration, or particle motion. Today we're going to think of it as a bug crawling along a horizontal surface. So a bug crawling along the chalk tray or whatever on the board. Okay, but the three equations we're going to use, the first is going to be a position equation. Today I think we call it x of t, so it's the x position as a function of time. If it's a height thing, you can see y of t if it's something up in the air. Sometimes you'll even see s of t. So this just gives you the position, right, from some set position called 0. You can think of it, 0 as maybe the origin, and the different positions as positions along the x-axis if you wanted to, or just a number line. Now, what we want to look at primarily is the derivative of the position, which is the velocity function. That's the velocity function. So whether we have a graph for position, we can think about what its graph would look, or what its derivative would look like in terms of slopes of tangent lines. If we have a function, we could take its derivative, and we'll get a new function for the velocity. And one thing to think about here is if you have a position time graph, so maybe this is position, this is time. Well, position might be in meters and time might be in seconds, correct? Would be reasonable units for a lot of science classes. You'll see those. So if you have that, if you think about, again, meters and seconds, so your position would be in meters, but if you think about the slope of this, if you find the slope of this curve, right, the instantaneous rate of change, the slope of the tangent line, it's going to be the change in y over the change in x, isn't it? And whatever we change in y is going to give us some meter measurement. So many meters minus so many other meters. So it'll be meters. And then on the bottom would be the change in x, right, which is the horizontal axis, which is our time axis, which would be in seconds. So you see why your velocity would be in meters per second. Right? It just has to go back to that slope equation, right? If you're looking at a position graph, right, and you want to find the average rate of change, it's going to be the vertical axis measurement divided by the horizontal axis measurement, or change in y over change in x, you could think of it that way. So that's our velocity. The other function we want is the second derivative of position, or the first derivative of velocity, and that's called the acceleration. Now, if we think about, again, in terms of units, if you think about a velocity function, we would have meters per second on our vertical axis. Down here would be time, so it would be in seconds. Well, if you found the average rate of change, right, or the instantaneous rate of change, the derivative, you would get the change would be meters per second divided by seconds, which is our unit for acceleration, which is meters per second squared. So we don't get super caught up in units in here near as much as you would in a science class, but if you can kind of it helps you kind of keep your finger on the pulse of what you're doing, right? If you kind of keep track of what those units are, maybe what they should be. But yeah, the biggest things are position function, its derivative is the velocity function, its derivative is the acceleration function. These are all going to be vectors, right, where they have a magnitude and direction, which all that really means is if your velocity is negative, you're going left. If your velocity is positive, you're going right. Right? So 5 meters per second means right at 5 meters per second. Negative 5 meters per second means you're still moving at 5 meters per second, but you're just moving left. Now, if you're in physics and you have like a 2 or 3 dimensional space, direction can be a little bit more challenging to write. Here we're just doing linear motion, so it should be pretty straightforward. Okay, and then the way that we can use these measurements to answer questions is this is from our packet here. If you see the bug is stopped, so we're talking about some bug crawling along the horizontal or the horizontal line here. Now, luckily, it would not be in meters per second probably for a bug, because that would be really scary if it was like, you know, like spiders jumping at you and stuff. It would be bad. This is a really slow, it's like a ladybug, you know, it's just like, it's going to like help your garden. It's a good bug. But if the bug is stopped in terms of position, velocity, acceleration, the way we can tell that is when velocity is equal to 0. Right? If your velocity is equal to 0, the object is stopped. Okay, that's the easiest way to figure out where that happens. Right? So again, the magnitude of velocity is called the speed. So your speed is 0, you're stopped. You're not going anywhere. So that's one thing we need to know. If the bug is moving right, when you have side-to-side motion, usually the right direction is considered positive. So you could tell the bug is moving right when the velocity is greater than 0. The velocity, which is the derivative of the position function, right? So we'll see. Now, a lot of this, the challenge is going to be you're going to be given different graphs and asked different questions. And you kind of really have to focus in on what you're given as a key. How about the bug is moving to the left? That would be when the velocity is less than 0. It's less than 0. The bug turns around. So I have to pretend I'm the bug here, but if I'm moving to the right, I have a positive velocity, correct? And then if I turn around, I would move left, so now I have a negative velocity, right? So I changed direction, the velocity went from positive to negative, or could it go from negative to positive? Would that be changing directions? Sure. Now what if the velocity just becomes 0? So what if I'm walking to the right, and then I stop, and then I start walking again? Did I change direction? No, so it's not enough for velocity to be 0 to indicate it turns around. But the velocity must change signs, right? Either goes from positive to negative or from negative to positive. Okay, if it just gets to 0 and then starts again in the same direction, it just means that you stopped. Last couple here, the bug is speeding up. This is where, at times, maybe the way that you talked about this in an earlier physics class that worked for there may not work for here. Here in calc, we're going to be pretty specific, but we define that when the object, or the bug in this case, is speeding up, is when the velocity and the acceleration have the same sign. So this would be when V and A have the same sign. Right? So if they're both positive, that means it's speeding up. If they're both negative, that means it's speeding up. Now if they're both positive, it means it's speeding up as it moves to the right. If they're both negative, it's speeding up as it moves to the left. So just be careful there. And then the bug is slowing down. That would be when V and A have opposite signs. So when the velocity and acceleration have opposite signs, it means that it's slowing down. Again, it could be moving in the positive direction and slowing down. It could be moving in the negative direction and slowing down. What I do, if that's the one, if you tend to have any trouble thinking about that, I think a nice little demonstration is I just have this little eraser here. And I know that the acceleration acting on this right now is negative 9.8 meters per second squared, right? The force due to gravity. If I drop it, it falls on the ground. But we expected that. But if you think about it, when you throw this up, it has a positive velocity. and then it stops, and then it starts coming back down, correct? But as I throw it up, is it slowing down the whole time it's going up? Well, sure, because once it leaves my hand, it starts slowing down. Oh, and it starts bouncing around the room. But it's going to slow down as it goes up, because if it sped up, right, it would just like shoot off into space, and that would just be weird. There'd be erasers flying around the earth. It'd be like an eraser belt or something. I don't know if that would be good or bad. But because it's slowing down, because even though the velocity is up, a positive direction, the acceleration is still negative, so it's slowing down. Now once it gets here, it has a zero velocity, then it starts to fall. It has a negative velocity, but it's speeding up, correct? Because the velocity and the acceleration are both negative, which indicates it's speeding up. So, but again, if you're asked when it's speeding up, you're looking for the velocity and the acceleration to have the same sign. Slowing down, the velocity and acceleration have opposite signs. It's not enough to say I looked at the graph and it's moving towards the axis or away from the axis, which are actually true, but we want to justify it in terms of our first and second derivative of position, would be the difference here. Okay, for our first example, a bug is moving along the x-axis for a time 0 less than or equal to t is less than or equal to 8. Its position on the x-axis is given by this function. Again, x is the name of the function, which is kind of different for us, right? T is the input variable. So x of t, 1/3 t cubed minus 7/2 t squared plus 12t plus 2. So we're asked some questions here. The first is, what is the position of the bug at time when it starts moving? Or starts walking. So with this, that would be at time 0, correct? Because this was defined, again, from 0 to 8 seconds. So the initial position would be the position at time 0, and position is just given by this function. So we would say that would be x of 0 is going to be 2. Put 0 in there for all the t's, you just get 2. Now, I don't think we ask it on this paper, but a question that comes up a lot is that, you know, from time 0 to time, or, you know, at time 5, what's the displacement? Displacement is the change from original, right? So if you wanted to find the displacement at time 5 seconds, you'd figure out the position at time 5, and then you'd subtract 2 from it, because you have to consider the initial position in terms of displacement. If it just wanted the position at times 5, you just plug 5 in there and you'd get a value, and that would be the position. So just be aware when you see the word displacement, it's the change in x. B says, at what time is the bug stopped? Timer times. Is the bug stopped? So now we saw from our table that the bug will be stopped when the velocity is equal to 0. So we need to find the velocity function. Now thankfully, we have a function we can take the derivative of pretty easily. So b of t, well, you'll get t cubed when you take its derivative, it'll become 3t squared. So 1/3 times 3 is just 1, so we get t squared. A negative 7/2 t squared, when we take its derivative, this will be negative 7/2 times 2t, so the 2's will cancel, and we'll get negative 7t. The derivative of 12t is just 12. The derivative of 2 is just 0. So here's our velocity function, right? It's a nice quadratic. We want to figure out when it's 0. Well, if you notice here, this just factors. Good old product sum factoring. So this equals 0 when t is at 4 or t is at 3. So at time 3 seconds and 4 seconds, if that's what the times are in, it never really stated, the bug would be stopped. Any questions there? And then lastly, on what interval is the bug walking to the left? Well, if we know walking to the left, that means we have a negative velocity, right? It's walking left. So what I would do here is this velocity function, this is just a parabola, correct? And we know the 2x intercepts, and we know it has to open up. So our graph of our velocity function, I'm going to label the y-axis as v of t to remind myself it is velocity. Oh, I guess I could do a little better graph here. But if we think about this, it only goes out to 8 seconds. We have zeros at 3 and 4. Again, we know it's a parabola that opens up, so it's going to look something like that. But it's going to be positive everywhere except between 3 and 4. Right? So we would say that on what interval is the bug walking to the left? That would be when the velocity is negative. So that would be from 3 to 4 would be when it's walking left. Now you really wouldn't include, you'd say between 3 and 4 seconds if it was in seconds, or 3 and 4 minutes if it was in minutes. But we're able to get this sketch, correct? Now, what that means though is if we would have graphed this original function, right, this would be some cubic, right? This would have a negative slope between 3 and 4, right? Because that's where because the velocity is negative there. Its derivative is negative, so this must have had a negative slope there. Doesn't mean the position's negative or the position's positive, it just means that it's changing in the negative direction. So it has a negative slope for the original position function. The velocity function would just be negative, just below the x-axis. That's how we can do that. So here's our second example. We have this graph. It states here, this is the velocity graph, right? So if you tried to make, if you think it's the wrong graph, you're really going to not be correct. Right? You're going to have to make a lot of other mistakes to get the right answer, which we try to avoid, multiple mistakes. But the first thing we're asked to find for part A is it asks us to find v of 3 and v of 11. So that would be the velocity at time 3. This is the velocity graph. So the velocity at time 3 would be 6. I went ahead and labeled these. So that would be 6. The velocity at time 11, that's over here, and that should be at -2. So at 3 seconds, it's moving to the right. At 11 seconds, it's moving to the left. That's what that tells us. For part B, ask us about some acceleration. What's a of 1, a of 5, and a of 3? So now we know the acceleration is the derivative of the velocity. So if this is the velocity graph, the acceleration is the slopes of the velocity graph. Now here we have a bunch of line segments, so finding slopes is not that big a deal. We could do that pretty easily. So at time 1, we still use the same x-axis. We were at this point here. But if we look, that there's a slope of a tangent line there. Everything on this point has a slope of, it rises 6 over 3, so it would have a slope of 2, wouldn't it? So the acceleration at time 1 would be 6 divided by 3, which would be 2. Right, so if the velocities were meters per second, this would be meters per second squared. Right, if this is inches per minute, this would be inches per minute squared. Because right? You're finding a rate of change, right? The change in y over the change in x. A of 5, well, that would be up here where it's horizontal. We know the tangent, the slope of the tangent of a horizontal would just be 0. So that means the velocity is not changing there, which is what we see. And then a of 3. Any ideas on what a of 3 would be? It's kind of a tricky one, right? Well, with it, because it's right there on this corner, isn't it? Now, the easy answer is if you think back to differentiability, we said that any corners, cusps, vertical tangents, or discontinuities are not differentiable, right? You can't find the derivative there. So the acceleration is the derivative, right, of velocity. So if the velocity has a corner, that means our acceleration is going to be undefined. So this would be undefined. Another way to think about it, though, is at that point, at this point 3, 6, right, we know that the definition of derivative is a limit, correct? And we know that it's the limit of the tangent lines as you approach this. So let's think, as we go at this point, our left-hand limit would be 2 for that slope, wouldn't it? Our right-hand limit would be 0. So the right-hand limit and the left-hand limit are different, so the two-sided limit does not exist. The derivative is the two-sided limit, so the derivative does not exist, or is undefined. It's kind of the way we can, two different ways to kind of argue that. Corner, that it's a corner is the easiest way by far, but it's because of that limit argument. All right, C asks us, at what time does the bug turn around? When does the bug turn around? And now if you're asked this on a test too, it might say, you know, when does the bug turn around? We're looking for a time. We're not saying, well, it turns around when it goes from one direction to the other. Like, I know what turn around means. So it's actually saying, at what time does it turn around? Okay, and we know that when whatever, the particle, the bug, turns around when the velocity goes either from negative to positive or from positive to negative. So where does that happen on our graph here? Would be at 9, correct? Because to the left of 9 it's positive, to the right of 9 it's negative. So that would be at t equals 9. Could we also say 0? No, the graph stops there. It doesn't turn around. We just know at time 0 it has a velocity of 0. How about time 13? Again, it stops. This is only for 0 to 13. We have no information what happens at 13.1 seconds or 13.1 minutes. We don't know. It's not a thing that we know. So just be at time equals 9. And on what interval does the bug have a negative acceleration? So when does the bug have a negative acceleration? Well, what's acceleration? It's the slope of the velocity, correct? So what it's really saying is when does that graph have a negative slope, right? When's it decreasing? Does it have a negative slope? So that would be from 7 to 10. So that's something. Now, another question that I think is worth looking at now, but it didn't ask it on here, is when is the bug slowing down? When's it slowing down? When's it speeding up? So let's get rid of these. Let's say, when's it slowing down? And when is it speeding up? Because that could be a tricky question for people here. So when it's speeding up, remember the velocity and the acceleration have the same value, don't they? So in this case, and I actually on here, it might even be worthwhile to write them, but for this segment, the slope is 2, isn't it? Right? So is the acceleration positive and the velocity positive right here? Sure, they're both positive, so that means it's speeding up from 0 to 3 seconds. Now, from 3 to 7 seconds, the slope is 0. So the acceleration is 0. So they don't have the same sign, right? It's a constant velocity. It's not speeding up, it's not slowing down. There's no acceleration, so it's neither slowing up nor speeding. Speeding up or slowing down. So now for this segment here, we dropped, 9 units in a space of 3, so that would be the slope there is -3. Now if we look, this is a negative acceleration, And then from 7 to 9, it still has a positive velocity, doesn't it? So we would say that from 7 to 9, it's slowing down. Right? The velocity tells us it's moving to the right, but the acceleration is the opposite direction. That way, you know, it's slowing down. Now what about from 9 to 10? Is the slope still negative? Is the velocity now negative? Yes, so there it's speeding up from 9 to 10, right? Because the signs are in agreement, right? They're both negative. Velocity and acceleration are both negative, it's speeding up. From 0 to 3, they're both positive, it's speeding up. And then from 10 to 13 seconds, we have a negative velocity, but we have a positive acceleration. Opposite signs, so that would be from 10 to 13, it's also slowing down. So slowing down or speeding up doesn't matter which direction you're moving, it just matters, do the velocity and acceleration have the same sign? Then it's speeding up. Do they have opposite signs? It's slowing down. So there we go.